numbers in to the computer. That's an analog to digital conversion. We fed an analog signal in and we got a digital result to deal with.
So the accuracy of the representation of the analog input would be very dependent upon the size of the time slices. The more rapidly you can actually see it on that original graph. When I was moving it very slowly, it gets a fair representation of moving it. When I moved it very quickly, obviously I was moving it further in the time slice that was allowed.
That's the major problem with analog devices. You must sample very frequently if you're to get an accurate representation. So two analog inputs there we've dealt with.
Well, what about analog output?
Okay, there are, on this computer, we've got some analog outputs set up. We've actually arranged two outputs. The machine can produce music, and it can also change lights. Now, lights normally go on and off in just a digital form, either on or off. But you can actually make the computer fade them up and down. Can you push some of the buttons? That's right, produces sound, which is analog, and music. Now, if you press the button slowly, you'll be able to see the lights fading up and down. Quite different from the digital world.
Well, thank you, John. And most things that can vary can be turned into electrical signals, which can be fed into the computer. And if we combine this ability to switch things on and off, we can begin to see how the computer can control, say, a robot, and do some of the things that we can do and which we take so much for granted, like moving our hands. There are two major differences between animals and ourselves. One is the brain, our intellect, if you like, and the other one is the hand. We can use it to hold tools, we can use it to play musical instruments, we can use it to write poetry, or we can even give signals with it. If you lose one hand, it's bad news. If you lose both hands, it's an absolute disaster. And for centuries, we've looked for artificial hands. First, it was a hook, and then a sort of clamp, which you could seize things with. It was slow, it was ugly, and nobody liked to use them. But much of the action of the hand is almost a reflex reaction. If you put something in the palm, it will clasp it. And it's in that area that we can start and make use of the power of a microcomputer. Now, here on my arm, imagine that I've lost my hand, thank goodness I haven't, but we're taking signals from the muscle on the top of my arm and the muscle on the bottom. And we can see the level of these signals by looking at the oscilloscope. By simply moving my hand like this, I get one signal, and by moving it that way, I get another signal. And of course, I can have positions in between this, and this can be used to command an artificial hand. And this is quite a unique piece of equipment and very, very sophisticated in what it can do. The control you have is almost uncanny, and it can almost follow exactly the movements of my hand as I open and close them. But of course, you don't need a hand. I could do that just by tensing the muscles and relax them, tense them and relax them. In fact, it would probably be a lot easier if I hadn't got a hand on at all, but that's a little bit too far for me to go. And I can close it very gently on something and pick it up and then put it back down again and release it. So there I'm using control, I'm controlling it. But in addition to that, this hand has 10 sensors on the palm, in the fingers and in the thumb, so that it will do things quite automatically outside my control. For example, if I take this screwdriver, I touch that sensor, the hand will automatically position itself to grip it. I then take over command myself and hold, and the fist will close over it, and it's extremely simple to use. I learned to use it in a matter of minutes, and automatically you can tap away and keep control over it, and then when you've done your job, you can open up the hand and get rid of the tool. There's an even more interesting sensor on this, and that's here in the thumb, and all it is a microphone underneath this piece of Velcro. And when I want to pinch something in between the fingers, I can pick up this piece of sponge like that, and as I pull this piece of sponge out, or attempt to, the sound is transmitted from this sensor here into the computer. When it hears the sound, it automatically tenses up the hands to stop me from withdrawing this piece of sponge. In other words, it's a complete feedback mechanism. No signal from my hand is affecting it. And I can simply open the fingers and let it drop. There's another sensor here on top. We touch that sensor like that, and the thumb comes over the top of the finger, and I can place, for example, a book in there, and then go into the hold, and it holds, and it will squeeze it, and then it can hold very firmly a tray or a book that you've picked up, and you can release it like that. But quite obviously, beautiful a hand as it is, nobody's going to want to walk around carrying this huge micro. In fact, this is just a development system. It's a 16-bit machine, and what will eventually happen once the programs have been totally perfected is that a special micro will be built and put into a box that size, so it can be put into the pocket and the hand controlled very elegantly. Well, that was a fairly complex system of sensors and control mechanisms. Let's have a look at something a bit more straightforward. Well, in the first series, we ran this demonstration, and it shows the same sort of logic that we saw in the hand. If something happens, then do one thing, otherwise do something else. And in this case, we're taking the temperature by this temperature sensor, and we're feeding it into the computer and displaying the temperature's number on the screen, and also running it as a graph. If the temperature falls below a certain level, we're going to switch on a heater. If it goes above a certain level, we're going to switch on a fan. And we can see if that works. We'll put it in some ice here. Immediately the temperature graph falls and the fan heater goes on. Put it in the hot water, get an immediate rise in temperature, the heater cuts off and the fan comes on. Well, John, how does it work?
Well, first of all, we have to sense what the temperature is and convert that temperature into a voltage, or at least produce a voltage proportional to temperature. Now, this basically is the device we use. It's a little integrated circuit, and you have to have a battery outside the circuit and a few other things. And all those are put together into a device like this. So there's several components in this device. And then that plugs into the analog input at the back there. So that's a way of sensing the temperature. In fact, we could stop the program running and I could tell it to print could you put it in the ice? Print add val 1, which will ask it to print the number that it's getting in from that input at the moment.
And presumably a higher value if you put it in the hot water.
That's right. So if we now ask it to print add val 1 again, you'll get a much higher value because there's a much higher voltage being produced by the temperature probe. So that gets it in. Now, if we have a look at the listing of the program, you'll see how we deal with those numbers. First of all, here we have temperature equals add val 1 divided by 36.5. And the 36.5 is just there to convert the number that the computer produces into a temperature in Celsius.
It's a straightforward relationship between the voltage and the temperature.
Yes, it's very linear indeed. And then down here you can see how we control the device.
Yes, I recognise this. If the temperature is less than 30 and the temperature is greater than 20, then the coordinates of 65,120 is equal to 0.
Right. The address 65,120, you may remember, we had that address for the output port, and we have got two wires connected onto the output port, one of which controls the fan and one of which controls the heater. And if you put 0 into this byte, then both of these will be switched off.
Well, there's the next temperature. If the temperature is greater than 31, in other words, it's hot, then the coordinates of 65,120 is equal to 1.
And in that case, a 1 would be placed here, and the fan switches on.
And if the temperature is less than 19, in other words, it's cold, coordinates of 65,120 equals 2.
Now, 2, translated into binary, we'll put a 1 in there and a 0 in there, and that will have the effect of turning the heater on, but not the fan.